Hi all, today we are going to discuss about string efficiency. So we know that if you are going above 33 kV, so greater than 33 kV, the pin insulators will not be efficient. So we go for suspension insulators, where the suspension insulators are called suspension because the insulator will suspend from the tower. That means they are oscillating or hanging from the tower. So in that case, let us assume 3 insulators are there. Let us assume the voltage across the first insulator is V1, second insulator is V2 and third insulator is V3, where the total voltage is V. We know the voltage that is impressed across this string of insulators will be the potential difference between the conductor voltage, what is the voltage at the conductor, and the ground. Or we can tell the voltage V is nothing but whatever is the line voltage, that line voltage you have to convert to the phase voltage. Because mostly we go for the star connection, that means this phase voltage or the voltage will be equal to VL divided by root 3. Please remember that if it is delta connection, that will be phase voltage is equal to line voltage only. So now this is came. So now because it is nothing but here there is a conductor, here there is another conductor, because this is also pin, between them some insulator is there, that forms a capacitance. So because of this the capacitance will be formed. So let us assume the capacitance of each disc, because capacitance is independent of the voltage that is applied. Let us assume this capacitance I am representing by C. So this capacitance is called as mutual capacitance, or it is also called as self capacitance. So let us assume the voltage distribution. Again I am taking the total voltage distribution will be equally divided among 3 because capacitance is same. So here also it will be, this will be V divided by 3 here. So similar is the case, V divided by 3. Voltage distribution is uniform because across each, because whatever the current that is passing, the charging current, that current will be same because all are connected in series. I hope it is clear up to now. But practically what happens, your tower whichever is hanging, because the tower also will be nearby, because tower structure practically will be like this. This will be the tower structure. So here they will be hanging and here the insulators will be hanging. So this is the tower. So because of this, between this pin and the tower, here also one capacitance will form. So the same thing I am representing here. Here let us assume there is a capacitance. So this is the second one. This is the third one. So each having a capacitance of C. So here is your supply voltage. So now what happens between this conductor, that means every pin as with respect to the ground, again one capacitance will be formed. This capacitance, in this capacitance what will happen? The air will act as a insulator and the pin of your insulator will act as one side, one terminal, and your tower will act as the second terminal or second plate of the capacitor. So capacitance will be formed here. How much capacitance will be formed? It depends on the distance from your cross arm or your insulator with respect to your tower. So let us assume this capacitance I am assuming that it is uniform, it is having a magnitude of C1. So this C1 is called as the shunt capacitance. C1 is called as the shunt capacitance. Now what happens? Let us assume the current I is taken from this. So let us assume that current across the third insulator I am taking as C3. So before that let us take the voltages. This is V1, this value is V2 and this value is V3. Okay, the current passing through the third insulator is I3. So whichever current when it comes here, the current will be divided. So this will be divided like this I2. Let us take capital I2 is passing here. Again after coming here, this will be divided like this. Here it will be I1 and capital I1 will be passing. So because of this shunt capacitance, you can see the current passing through each insulator is not same. When the current passing through each insulator is not same, we know that the capacitive reactance that multiplied by the capacitance gives the voltage across this. So we can tell that the voltage distribution across the strings will not be same. So you can see whichever the insulator is there in the lower side, that is carrying more current when compared to the insulator that is carrying the upper side. The voltage across any insulator can be obtained by voltage V is equal to, we know that the value of the current that is passing through it is multiplied by the capacitive reactance. Let us take for example the voltage that is passing through the third insulator V3, voltage across this insulator will be I3 multiplied by X3. So similar is the case, the voltage V2 I can write as I2 multiplied by XC because capacitance is same. Similarly voltage V1 I can write as I1 multiplied by XC, XC is same. So here you can see that the voltage across any insulator is directly proportional to the current passing through it, because we know the value of I3 is greater than I2 is greater than I1. So automatically the voltage drop across the third one will be greater than voltage drop across the second one is greater than voltage drop across the first one. That means the voltage distribution across the strings will not be uniform because of the formation of shunt capacitance. Let us try to summarize the point what we have seen till now. Then we will proceed for how to solve this problem. The voltage impressed on a string of suspension insulators does not distribute itself uniformly across the individual discs due to the presence of shunt capacitance. This is what we observed. Next, the disc near to the conductor has maximum voltage across it. As we move towards the cross arm, the voltage across each disc goes on decreasing, and the unit nearest to the conductor under maximum electrical stress, because maximum voltage drop is across that one only, and is likely to be punctured. Therefore, means must be provided to equalize the potential across each unit. That means the lower unit which is there near to the conductor will be stressed more. It will get punctured if you are using same value of capacitance. So, one option is there, you design your value of this insulators in such a way it can withstand that highest value of the voltage. If you are designing for highest value of the voltage, the each disc is not utilized properly. The how much extent the disc is utilized, that is given by the term string efficiency. So, string efficiency is the ratio of voltage across the string, what is your supply voltage or the voltage phase voltage, divided by n times the voltage across the disc near to the conductor, where n is the number of discs in the string. We know the voltage across the disc nearest to the conductor is highest. So, because of that non-uniform distribution, the string efficiency will be always less. So, you have to improve the string efficiency so that every disc will be properly used. So, the greater the string efficiency, more will be the uniform voltage distribution. So, let us see what will happen and how much will be the effect of this non-uniform distribution. So, for that, let us take C1 is equal to some K times of C. Let us assume the insulators are distributed like this. So, these are 3 insulators. So, 3 insulators are there. So, the capacitance will be formed between the conductor and this one. So, this is one capacitance. There will be capacitance here. There will be capacitance here. Okay, let us take this capacitance as C1. C1, this is the shunt capacitance, and the self or mutual capacitance I have represented here. So, total supply voltage I am taking as V, and out of this the voltage distribution, let us take this as V1. Let us take this as V2, let us take this as V3. Now, out of the current that is produced, let us assume the current I3 is there and this current is equal to I3, which are taken from the supply. So, from here onwards, out of this current I3, some current I2 is passing here and capital I2 is passing here. Similarly, I1 is passing here and capital I1 is passing here. So, here you have to remember that always this voltage across this shunt capacitance will be voltage at the pin and the reference point or the ground point. You can see this reference point is connected to this reference point. So, we can tell that these two are at the same potential. We have to calculate accordingly. So, let us keep the nodes as A, B, and let us take this node as C node, and there is a ground potential or the reference node. Now, starting from the cross arm or tower, the voltage across each unit is V1, V2 and V3 respectively. So, before proceeding, I want to tell you one thing. I am writing on the glass screen, so handwriting doesn't come properly. So, I am providing the complete handwriting material in the description below, description of this video. You can just go to the Google Drive link, you can download the complete material from there. Here you try to understand what I am teaching, and remaining material you can download from there. So, I am applying the KCL at node A. When you are applying the KCL at node A, so at node A the current entering is equal to I2 is equal to current leaving I1 plus small I1. So, this I can write as V omega C, that is V2 into omega into C, because I2 can be calculated from V2. V2 into omega C will be equal to I1 will be equal to V1 into omega C, and the capacitance C1, the first one, this I1 is passing through C1. C1 is connected between node A and the tower. So, this also having the voltage of V1 only. So, this will be V1 omega into K into C. So, from this I can write my voltage V2 is equal to V1 into 1 plus K. Let us take this as equation number 1. So, now similar way I am applying KCL at node B. So, when you are applying the KCL at node B, we will get the value I3 is equal to I2 plus small I2. So when this will be equal to, so let us take the I2. So I2 is producing a voltage of I3. So I3 is producing the voltage of V3. So V3 will be there here. So this will become equal to V3 into omega C is equal to the value of I2. I2 is producing a voltage of V2. So that's why it will become V2 omega C plus what is the voltage between this one, because I want to calculate the small I2, this point B and your tower. The point B and the tower, you can see this tower is nothing but the voltage at the ground potential or this potential. So whatever this voltage is there, this will be the voltage between B and tower. So that will be the responsible for production of the current I2. So what is the value of the total voltage here? It will be V1 plus V2. That's why I am taking the sum. So this will become V1 plus V2 multiplied by omega into C1. It is clear up to there. So this I can write as V2 omega C plus V1 plus V2 times of omega into, because C1 we can write as K times of C, so that we can simplify it. So from this I can write V3 is equal to V2 plus V1 plus V2 times of K, or otherwise this I can write as K times of V1 plus V2 into 1 plus K. V2 into 1 plus K. So this I can write as K times of V1. Now V2 I can represent in terms of V1. So if you represent in terms of V1, this will be V1 into 1 plus K whole square, or this I can write as V1 into K plus 1 plus K whole square. So this will be equal to V1 into 1 plus 3K plus K square. So this is the value of V3 we got. So let us take it as equation number 2. So if you want to calculate the total voltage across the string, total voltage across the string will be equal to V1 plus V2 plus V3. So before proceeding, you will get a doubt. There is a capacitance is formed here also, small I3 also. Why I am not taking this? Because remember here, this is directly connected to the conductor. It is not going to affect any voltage distribution across your string. So that's why I am not counting that one. No need to consider that one, because it is not related to any voltage drop across any string. So now let us proceed further. This will be V1 plus V1 into 1 plus K plus V1 into 1 plus 3K plus K square. This is what we get. So this I can write as V1 into 3 plus 4K plus K square, or this I can write as V1 into 1 plus K multiplied by 3 plus K. This is what we get. Let us take it as equation number 3. This is the total voltage. So from equation number 1, 2 and 3, I can tell that the ratio can be equated. V1 divided by 1 is equal to V2 divided by 1 plus K is equal to V3 divided by 1 plus 3K plus K square. This will be equal to total voltage divided by 1 plus K into 3 plus K. This is the way the voltage is divided across your string of the insulators. So we can tell that voltage across the top unit is V1 is equal to, I can tell it as V divided by 1 plus K into 3 plus K. I can calculate in this way. So voltage across the second string will be V2 is equal to V1 multiplied by 1 plus K, and the third one I can calculate voltage across the third string, if you know in terms of the voltage across the first one. So this I can write as V1 into 1 plus 3K plus K square. So you can see here, as you are going downwards towards the conductor, because the term K is added to 1. So 3K plus K square is added. As you are moving towards the conductor, the voltage is increasing across your insulators. So from this, I can tell my string efficiency is equal to voltage across string divided by n times of voltage across the string nearest to conductor. Voltage across the string nearest to conductor multiplied by 100, or we can tell voltage across the string is V. This will be multiplied by 100 divided by n times of voltage across the string, or 3 times, n is equal to 3 insulators here, multiplied by V3, or this I can write as V divided by 3 times of, if you are representing V3 in terms of V, so V3 will be V multiplied by, because this term will go there, because these two I can equate. So 1 plus 3K plus K square divided by, and next one what is there, 1 plus K into 3 plus K, 1 plus K into 3 plus k. This term comes, so this comes to the numerator. This will become 1 plus k into 3 plus k divided by 3 times of 1 plus 3k plus k square. This is the equation multiplied by 100. Because of this, the string efficiency will be always less than unity, or string efficiency is always less than 100%. That is going to affect. So let us make the observations from this, so that we will see what are the remedies for improving the string efficiency. So first one is, if the value of k, let us take for example k is equal to 0.2. I am just assuming it. Then if you calculate using this formula, you will get the voltage of V2 is equal to 1.2 times of V1, and the value of V3 will be 1.64 times of V1. So this clearly shows that the disk near to the conductor is having the highly stressed when compared to disk that is far away. So because of this, so much stress is applied on the conductor near to the, the insulator near to the conductor. So the second observation is, so the value of k is equal to C1 divided by C. So as the value of the k is increased, so automatically the string efficiency will goes on falling down. So more non-uniform distribution will be there. This is the second observation. And the third observation is, the inequality in voltage distribution increases with the number of disks. So that means this inequality increases with increase in the disk. Because practically we do for 132 kV, 220 kV and 400 kV lines. So in that case, the number of disk insulators are more. So as the insulators are more, the distribution becomes more non-uniform. So string efficiency falls down much more faster. So this is going to affect your utilization of your insulators. So how we can improve this? We can improve this by decreasing the value of k. We can make it by decreasing the value of k, or you design the insulators in such a way that across each insulator the voltage distribution will be same. So in that way you can design it. So these things are called as the methods to improve the string efficiency. So these things we are going to discuss in the tomorrow's class. I hope how the voltage is distributed across different string of the insulators, and what is string efficiency and what is the effect of the shunt capacitance on the voltage distribution is clear to you. So if you have any queries, you can leave your comments in the comment section below. I will answer to your queries from there. Thank you very much.